Okay, so my name is Chris Harshaw. We'll be talking about greedy methods for near-optimal submodular maximization. This is joint work with Moran Feldman and Amin Karpasi. Okay, so to begin, submodular functions are discrete functions that have this diminishing returns property. And so more precisely, it's a real-valued set function f. And we say it is submodular if for all sets A and B, where A is inside of P, the marginal gain I get by adding in elements to X to A is larger than the marginal gain I get from adding that same element to P. And we say that f is monotone if f of A is less than f of P. So intuitively, this just means that the adding things does not decrease our function value. So this diminishing returns property comes up a lot in machine learning, in decision making, and also classic combinatorial optimization. Now, when we talk about this optimization, we're going to use independence systems to describe our notion of feasible sets. So one example, and I'll define this, but one example is a cardinality constraint. That is all sets of a given size or less. Another example is the intersection of K matroids. And so an example of what this is suppose I have my ground set V here, and I have groups. Each point can belong to one or many groups. And for each group, I have a limit on how many points I can pick from that group. So here, if my limit is 2, this could be a feasible set, or this could be a feasible set as well. So now let's go ahead and define what these independence systems are. We're going to be looking at 2, but first, an independence system I is a set of subsets of our ground set V, such that I is non-empty, and for any B in I, all subsets are also in I. So if B is maximal in I, then we'll go ahead and call that a pace. So the first independent system that we're interested in is one that's called a K system, and that is that if the ratio of paces, their size, is less than or equal to K. Another type of independent system that we're looking at is the K extendable, and it goes like this. So suppose I have A, and I have B, and B is contained, or A is contained in P. I can pick any point in P, and adding it to A might make it not independent, but I can always remove at most K elements inside A and add E, and that will mean that it's still independent. So every K extendable system is a K system here, and there's lots of things like the matroid intersection, cardinality constraints, graph matchings, things that come up in scheduling. So K extendable captures a lot of what we're interested in, but K system is a larger, broader set of constraints. So the problem that we're interested in is given a finite ground set V of size n, we're wanting to maximize a submodular function subject to these independence system constraints. And so we're assuming we have oracle evaluations of f and of I. So this is actually NP hard, even when I is a simple cardinality constraint. So when we talk about algorithms for solving this, we're interested in their approximation ratios and also their time complexity. So the first easiest thing you might be interested in is the greedy algorithm, and that is just start with the empty set. And if there are elements that I can add that satisfy my constraints and have a positive increase in my function, go ahead and add those, and in particular add the one that maximizes that increase to my function. So how well does this greedy algorithm work? Well, it's well known that for monotone f, we achieve constant factor approximation ratios in our problem size. For k systems, you get an approximation of k plus 1, but for non-monotone f, greedy can perform arbitrarily poorly, so the existing algorithms require much more sophistication. So their approximation ratios are a little bit worse, and they have a multiplicative factor of k in their runtime here. So what our work does is that for general submodular functions, we show that a simple use of the greedy algorithm actually achieves near optimal performance. So there are two ways of doing this. The first is to run greedy a few times. The other way is to actually just sample your ground set and run greedy once. So this is a summary of those results here. So our randomized algorithm works on k extendable systems and achieves an approximation ratio of k plus 3. And so we've actually eliminated that multiplicative factor of k, and we can repeat greedy several times to work on a more general class. We achieve a little bit worse ratio here, and we incur a multiplicative factor of square root k. And to complement this, we also have hardness results that no polynomial time algorithm can do better than k plus 1/2. So in this sense here, our simple sample greedy is nearly optimal. So what is this algorithm? It's essentially just start with your ground set V. We're going to obtain a smaller ground set V prime by independently sampling each point with probability 1 over k plus 1. And then we're just going to run the greedy algorithm on this sub-sampled set here. So in expectation, we show that this achieves an approximation ratio of k plus 1 squared over k that is smaller than k plus 3, and it runs in nearly linear time. So this is the simplest algorithm that you could have. It has very nice guarantees. It scales to massive data sets, and you can actually run this many, many times. So you might want to sample, run, sample, run. So the second algorithm here is similar. So we're going to have this greedy solution here. We're going to run an unconstrained optimization inside this greedy. We're going to remove that from our ground set, run greedy again, do an unconstrained, and repeat this square root of k times. And so then we're going to return the sets that we've gotten in this way that maximize f. And so, all this guarantees depends on the subroutine you use for unconstrained submodular maximization. But using this one here, we can get the guaranteed approximation ratio and run time. So I'm out of time, but I'll point out that we also have these hardness results here that show that our algorithms are near optimal. So to summarize, the greedy algorithm is in general bad for non-monotone submodular functions, but just doing very simple invocations of the greedy algorithm, we can obtain near optimal performance. Thanks.
We have time for one quick question.
Yes.
One point I didn't understand the repeated greedy algorithm. How do you ensure the constraints are met because you have unconstrained?
Right. So we do the greedy, and so in greedy your constraints are met, and then we run an unconstrained just on the greedy. And so because you're in an independence system, everything in there should be, yeah. Thank you.